What's up everybody, and welcome to part 13 of my Basics of Deep Learning series. In the previous video, we left off at the point where we've written down all the equations that we need to implement the backpropagation algorithm in code. And this is what we're going to do now. So let's get over to the Jupyter notebook. And here I've already made some preparations. So I've loaded in the iris flower dataset, and I've selected the flowers that we've been working with all the time, or the whole time. And then I've also created the label matrix and our input matrix. Then I've defined the Sigmoid function, and here I've set some parameters. So I've set the learning rate to 0.1, so this learning rate here. And then I've defined capital N, which comes from our mean squared error function, and which is simply the number of elements that we have in our label matrix, which corresponds obviously to the number of elements that we have in our then output matrix. And these elements is just the number of examples times the number of nodes. And then here I've also defined the number of nodes that we have in each layer. So in the input layer we have 4 nodes, in the hidden layer 2, and in the output layer we have 3 nodes. And then here I've initialized some random weights. So weight matrix 1 is going to be a 4x2 matrix because it goes from 4 nodes to 2. And weight matrix 2 is going to be a 2x3 matrix because it goes from those 2 nodes to those 3 nodes. And then here I've written down the feed-forward algorithm. So if I run this, then I will create the output layer outputs, and with those then and the labels we can then calculate the mean squared error. And here the mean squared error is then simply 0.138 like we've had in this diagram. So now we can start to implement the backpropagation algorithm. So let's make a comment here, backpropagation. And to implement that, we actually just need to implement those equations here. So first we're going to say output layer error equals the output layer outputs minus the label matrix. So output layer outputs minus y. Then in the next step, output layer delta. This equals the output layer error times the output layer outputs times 1 minus the output layer outputs. And with those now we can calculate the update, the weight matrix 2 update. So let's make another comment for that, and here we're going to write weights update, and then going to say weights 2 update equals this matrix modification here. So we're going to say np dot hidden layer outputs transposed, and then the output layer delta, and this then we divide by capital N. And then to actually execute this weight update, we then have to do this calculation here. So we're going to say weights 2, and let's also say here weights 2, and then we're going to say weights 2 equals weights 2 minus learning rate times our weights 2 update. So that's the first update. Then here going through with the backpropagation, we're going to then say hidden layer error equals np dot of the output layer data and weight matrix 2 transposed, and then hidden layer delta equals the hidden layer error times the hidden layer outputs times 1 minus the hidden layer outputs. And with that, then we can create our weight matrix 2 updates. So we're going to say weights 1 update equals mp dot of our input matrix transposed and hidden layer delta. And this then we divide by n. And then here we can say weights 1 equals weights 1 minus the learning rate times weights 1 update. And now if we run this, then we should update our weight matrices, and then we should be able to make better predictions. So the output layer outputs should be more closer to our targets, to our labels. So if you run the feed-forward algorithm again, this time with the updated weights, then here the mean squared error should be somewhat lower. And let's see if that's the case. And as you can see, it is somewhat lower, but the improvement is only very small, which means that we have to run the feed-forward and backpropagation algorithms many more times. So the question then is, how often should we run them? And one approach might be to say, okay, let's run them until the mean squared error is 0. But this doesn't really work because, as we've seen in one of the previous videos, one characteristic of the gradient descent algorithm is that we will only get an approximation for the minimum of the function. So we might never reach a mean squared error of 0. And furthermore, as we get closer and closer to the minimum, the steps that we take get smaller and smaller. So in this area here, when we are very close to the minimum, we are going to take many steps, which might take a long time to run, but the mean squared error then wouldn't change that much. And this begs the question, when should we stop training our neural net? And this will be the topic of the upcoming video. So thanks for watching, and hopefully I will see you in the next video.